In this video, we want to prove some properties about conjugate of complex numbers. These properties are really useful for simplifying expressions in complex numbers. We want to prove that conjugate of z1 plus z2 is equal to conjugate of z1 plus conjugate of z2, and other properties that you can see here. To prove that conjugate of z1 plus z2 is equal to conjugate of z1 plus conjugate of z2, we suppose z1, which is a complex number, as x1 plus iy1. We know that any complex number can be represented in the form of x1 plus iy1. So we suppose z1 to be x1 plus iy1, and we suppose x2, and we suppose z2 as x2 plus iy2. For all parts of this proof, to prove A, B, C, and D, we do the same process. We suppose Z1 and Z2 two complex numbers in these forms, and then by substitution in both sides of the equations, we will show that the two sides are equal to each other. If Z1 is x1 plus iy1 and Z2 is x2 plus iy2, let's see what is Z1 plus Z2 conjugate. Here, we have to add z1 and z2 to each other, then we have to calculate its conjugate. What is the sum of these two complex numbers? We know that to add two complex numbers, we add real to the real part and imaginary to the imaginary part. So, the sum of these two complex numbers is x1 plus x2, which if you want, you can put a bracket for that, plus I times y1 plus y2. This is the sum of z1 and z2. Now, we have to calculate the conjugate of this complex number here. We know that conjugate of a complex number is another complex number that the difference between these two is the sign here. Because here is plus, so the conjugate of this complex number is same complex number but with a minus. So it equals to x1 plus x2 minus I times y1 plus y2. So this is the value of the left side of this identity. Now let's see what is the value of the right side of this identity. So we want to find z1 conjugate plus z2 conjugate. Because z1 is this, so z1 conjugate is x1 minus iy1. What is z2 conjugate? x2 minus iy2. Now if we add these two, we add real to real and imaginary to the imaginary. So it equals to x1 plus x2, we add real to real, and we have negative iy1, and minus iy2, it would be minus I bracket y1 plus y2. And by comparing equation 1 and equation 2, we can see that these two are equal. So this means that z1 plus z2 conjugate is the same as z1 conjugate plus z2 conjugate. So by comparing these two relations, we can conclude that this identity is right. Here, I highly recommend you to pause the video and try to prove part B by yourself. It is very similar to part A. Now let's prove part B of this question. We want to prove that conjugate of z1 minus z2 is equal to conjugate of z1 minus conjugate of z2. Again, we suppose z1 to be this, z2 to be that, and then we start proving. Let's start with calculating the left side of this identity. First, we want to see what would be the conjugate of z1 minus z2. First, we have to subtract z2 from z1. So if we subtract this from this, we have x1 minus x2 plus I times y1 minus y2. But what is the conjugate of this expression? The conjugate of this expression is simply same expression, x1 minus x2 I times y1 minus y2, but we have to make the between negative. Now let's see what is the value of the other side. What is conjugate of z1 minus conjugate of z2? z1 is x1 plus y1. The conjugate of z1 is x1 minus y1 minus z2 conjugate, which is x2 minus y2. If we subtract, then we have x1 minus x2. We subtract real from real, and then minus I times y1 minus I y1 plus I. So if we factor, please pay attention, we factor negative I here, then we have y1, so we have to put y1 here. And if we factor negative I, don't forget we have a negative here, then we have minus y2. And as you can see, these two relations are equal to each other again, and this proves that this relation is also true. Let me explain here again what happened from here to here. In here we have negative I y1. If we multiply this negative here, we have plus I y2. If we factor negative I from these two terms, then from the first term we have y1, and because we factor a negative I, this y2 would be negative y2. This is another way to get from this to that. Now we want to prove relation C, which is a little harder. This is not as straightforward, so much like part A and B. So we want to prove that z1 times by z2 conjugate is equal to conjugate of z1 times by conjugate of z2. Again, we suppose z1 as x1 plus I y1, and we suppose z2 as x2 plus I y2. And we are going to calculate the left side and right side of this relation. So we want to see what is z1 times z2 conjugate. It equals to conjugate of multiplying these two complex numbers by each other. x1 plus I y1 times by x2 plus I y2. We have to multiply these two complex numbers by each other. It equals to x1 x2, then x1 times I y2 would be I x1 y2, and also we have I y1 x2, and we have I y1 times I y2 would be I to the 2, and I to the 2 is negative 1, so we have negative 1 times by y1 y2. So when we multiply I y1 by I y2, the answer is negative y1 y2. Because when we multiply this by this, we have I2 y1 y2, and this is negative 1. I squared is negative 1. Now we have to calculate the conjugate of this complex number that we have here. We want to calculate conjugate of this. To find the conjugate of this, first, let's rewrite this in a proper form. x1, x2 minus y1, y2 plus I times x1, y2 plus x2, y1. If you wonder why I wrote this number in this form, because I want to group the real parts here, and then the imaginary parts in another group here. We factor I from these two terms, and then we have x1 y2 plus x2 y1. Now the conjugate of this expression is simply x1 x2 minus y1 y2 minus I times x1 y2 plus x2 y1. This is the conjugate of this number. And now let's calculate the other side. Now we want to find what is z1 conjugate times by z2 conjugate. The conjugate of z1 is x1 minus I y1, and the conjugate of z2 is this. Multiply the brackets, then we have x1 x2 minus I x1 y2 minus I y1 x2 minus I y1 times y minus I y2 would be plus I squared y1 y2. And I squared is negative 1, so we have minus y1 y2 again. When we multiply this by this, the answer would be I squared y1 y2, but I squared is negative 1, so the answer is negative y1 y2. Now we group the real parts in this form, and if we factor a negative I, then we have x1 y2 plus x2 y1. Compare these two equations, 1 and equation 2. As you can see, this expression is exactly this expression. So this shows that z1 z2 conjugate is always equal to z1 conjugate times by z2 conjugate. And this completes the proof of this part of the question. Now we want to prove that z1 divided by z2 conjugate of division of two complex numbers is equal to conjugate of numerator divided by the conjugate of denominator. To prove this, again we suppose z1 as x1 plus I y1, and we suppose z2 as x2 plus I y2. Now let's calculate the left side and the right side. z1 divided by z2 conjugate would be equal to x1 plus I y1 divided by x2 plus I y2 conjugate. We have to divide these two complex numbers by each other first, and then we have to calculate its conjugate. Remember that to divide two complex numbers, to divide a complex number by another complex number, the method is to multiply numerator and denominator by the conjugate of the denominator. What is conjugate of x2 plus I y2? x2 minus I y2. And of course, the conjugate of this. So, for simplifying this expression, this division, we multiply numerator and denominator by the conjugate of the denominator. This is the process of dividing two complex numbers. Now we start multiplying numerator by numerator and denominator by denominator. For numerator, if we multiply, we have x1, x2 minus x1 times I y2 would be minus ix1 y2, and then we have plus ix2 y1 or iy1 x2, the order of multiplication doesn't matter. And iy1 times by negative iy2 would be plus y1 y2. Why? When we multiply iy1 by negative iy2, this equals negative I squared y1 y2. But we know that I to the 2 is negative 1. Negative 1 times negative would be 1. So the answer is only y1 y2. So we have plus y1 y2. What about denominator? For multiplying this complex number by its conjugate, we know that we can simply multiply real by real. So we have x2 to the 2 minus iy2 times by iy2 would be I to the 2 y. When we multiply this by this, it would be I2 y2 to the 2. This is negative 1, but we have a negative between, so when we multiply denominator by denominator, the answer would be plus y2 to the 2. The answer of multiplying this by this is simply this. If you want, you can multiply term by term, but this is the answer at the end. And I have repeated this thing in all of my videos about complex numbers, that when you multiply a complex number by its conjugate, you don't really need to multiply them by each other. Always the answer, this answer, is real to the 2 plus imaginary part, which is y2 to the 2. You don't need to really multiply a number by its conjugate. Simply raise real to the 2 plus imaginary to the 2. For example, suppose in a question you want to calculate what is 2 minus 3i times 2 plus 3i. Don't start multiplying anything. The answer is always real to the 2 plus imaginary to the 2. So the answer is 13. Keep this in your head. It simplifies the process of multiplying two complex numbers. Sometimes, of course, when you multiply a complex number by its conjugate. Now, let's group in numerator real parts and imaginary parts in two different groups. So, we have in numerator x1, x2 plus y1, y2. And also, if you factor in negative I in numerator, we have negative I times x1, y2 plus, because we factor in negative I, the second term in the bracket would be negative I, negative x2, y1. Because when we multiply this negative inside, we have this positive here. All over the denominator. All of this over x2 to the 2 plus y2 to the 2. But don't forget, we have to calculate the conjugate of this. Remember that the conjugate of a complex number is simply same number, but we have to change the sign between them. So, here, let me ask you a question. Can you tell me in this complex number here, in this complex number, what is the real part? Attention, I'm not talking about just numerator, I'm talking about all of these bracket. What is the real part? Real part of this complex number is all of this. This is the real part. And what is imaginary part of this complex number? The real part is the first bracket again, over the number. But what is the imaginary part? Imaginary part is this negative, all of this, over this. because basically we have to divide numerator by the denominator. So before finding the conjugate of this complex number in the bracket, let's separate numerator by denominator to separate real parts and imaginary parts. So we can write this in the form of x1, x2 plus y1, y2 all over x2 to the 2 plus y2 to the 2 and minus I times by x1 y2 minus x2 y1 all over x2 to the 2 plus y2 to the 2. Maybe it's not a bad idea to write this first and then write I here. But I leave it like this here. Now let's find what is it. Oh, we forgot to find the conjugate of this. We have to find the conjugate of it. What is conjugate of this expression? This is real. This is imaginary. Conjugate would be just change this minus to plus. So the conjugate is x1, x2 plus y1, y2 all over x2 to the 2 plus y2 to the 2 plus I times x1, y2 minus x2, y1 all over x2 to the 2 plus y2 to the 2. So this is the answer for the left side. Now let's calculate the right side of this relation. So we want to know what would be z1 conjugate over z2 conjugate. z1 conjugate is the conjugate of this expression. And conjugate of this expression is x1 minus iy1. And conjugate of z2 would be x2 minus iy2. To divide these two, we multiply numerator and denominator by the conjugate of the denominator, which is this. Now let's multiply numerator by numerator, denominator by denominator. Can you tell me what is the answer of multiplying this by this right away? Yes, it is x2 to the 2 plus y2 to the 2. What about numerator? We multiply term by term. If we multiply numerator, we have x1, x2. Now if we multiply this by this, we have ix1, y2. By multiplying this by this, we have minus ix2, y1. And finally, we have minus iy1 times by iy2, which at the end would be minus i2 y1 by 2, but I to the 2 is negative 1 times by another negative that we have, so it would be at the end plus y1 by 2. Now let's group real parts by each other and let's factor I from these two terms. If we factor I from these two terms, then we have x1 y2 minus x2 y1. And please pay attention, here I forgot here the index of y here. It should be y sub 1. So here it's y1 here. Let's continue our process here. Then the denominator is x2 to the 2 plus y2 to the 2. Now, similar to the previous part, we divide this by the denominator and we divide this by the denominator because we want to get to this form and we want to show that they are equal. If we separate, we have x1, x2 plus y1, y2 all over x2 to the 2 plus y2 to the 2. And we have plus I times x1, y2 minus x2, y1 all over x2 to the 2 plus y2 to the 2. By comparing relation 1 and relation 2, we can conclude that this is equal to this. Because, as we can see, The answer for both of them is the same. This expression is exactly equal to this expression here. And this shows that for division of two complex numbers, we can separate the conjugate. Now we want to prove this relation. Z1, Z2, Z3 conjugate is equal to Z1 conjugate times by Z2 conjugate times by Z3 conjugate. So we want to prove that not only for two numbers, for three or even more complex numbers, we have similar relation for conjugate. We can separate basically conjugate over the complex numbers in algebraic operations. Maybe you are thinking to suppose Z1 as x1 plus iy1, Z2 equals to something, Z3 equal to something, and then show that the two sides are equal. But attention, there is easier way to prove this relation. Now we have proved something, and when you prove something in mathematics, then you can use it everywhere to prove other things. So you don't need to start from scratch. Right now we have proved this relation. We have proved what? We have proved that Z1 Z2 conjugate is equal to Z1 conjugate times by Z2 conjugate. But how we can use this to prove this relation? How to use this relation to prove that relation? Let me show you. This relation is only for two complex numbers that you can separate. So we have to try to make this expression in the left as two complex numbers, because we have Z1, Z2, Z3. It's three complex numbers. How we can make it like a two complex numbers? In this way. Z1, Z2, Z3 is basically Z1, which is a complex number, times by Z2, Z3. So we group Z2, Z3 in a bracket like this. Now we say this is a complex number, so this plays the role of Z1. And this is another complex number, it plays the role of Z2. And for two complex numbers, attention, these are now two complex numbers, we can separate the conjugate. So now we say this equals to Z1 conjugate times by Z2, Z3 conjugate. Here, please pay attention. To write this, we use this relation. You should explain that. With the aim of this relation, we can write this in this form. Now, here, let me write this a little better. Now here, again for this, we use this relation. So we use that relation twice. So again we write Z1 here. Now for this part, again we use this relation. And we say Z2, Z3 conjugate is Z2 conjugate times by Z3 conjugate. And this completes the proof of this part of the question. Show that Z4, Z to the power of 4, which means that Z times Z times Z times Z conjugate is the same as Z conjugate to the power of 4. Again, to prove this, you don't need to start from scratch. You can say, we know that Z1 times Z2 for two complex numbers, we can write this as Z1 conjugate times by Z2 conjugate. You can use this relation from now on everywhere you want. But Z to the 4 is Z times Z times Z times Z. But this rule is for only two complex numbers. So we have to try to write Z to the 4 as the product of two complex numbers. How? It's very easy. So we start the proof in this way. We say Z4 is basically z2 times by z2. Now consider this as z1 in your head and consider this as z2. Based on this relation, we can write this as z2 conjugate times by z2 conjugate. Repeat the process for this part now. z2 is z times z. z2 is z times z. For this, again we use this relation, and so we can write this in the form of z conjugate times z conjugate times by, now for the other part, z conjugate times by z conjugate. Now we have z conjugate times by itself 4 times. This equals what? This equals z conjugate to the power of 4. And this completes the proof of this part. In general, with the induction method, which is a proof method in mathematics, we can prove that z to the n conjugate is z conjugate to the power of n, which means that we can move the power to the outside of the conjugate. So in general, not only for power 4 or 3 or 5, for any power, we can bring the power out of the conjugate. But for the proof of this, we need to be familiar with the induction method for proof. I'll try to prove this in general with the induction method in another video, but here in this video I'm not going to show it to you here. I hope by watching this video, now you are more familiar with the properties of the conjugate of complex numbers, and you have learned how to prove these properties. If you like this video, please subscribe in my channel.